All right, today we're going to tear down a really classic system design problem. How do you build a service that can reliably run millions or even billions of tasks sometime in the future? This is the engine that powers so many features you probably use every single day without even thinking about it.
I mean, you've definitely used one of these, right? When you schedule an email in Gmail to send later, or you tell Slack to remind you about something tomorrow morning, or even when a customer service line says, we'll call you back in 10 minutes. It's all the same fundamental architecture that we're about to break down right now.
So let's get into it. The real trick here, isn't just about scheduling one single task. That's easy. It's about building a system that can handle a massive, massive volume of these tasks without even breaking a sweat. And when I say massive, I mean it. We're talking about systems that need to manage, potentially, billions of tasks waiting to be executed. At that kind of scale, the simple solutions don't just get a little slow. They completely fall over. They crash and burn, risking data loss and, honestly, breaking your users' trust.
So, what are our non-negotiables? What are the ground rules for building this thing? First, reliability. A scheduled task is basically a promise you make to your user. It has to run, period, even if a server goes down. Second, scalability. The system needs to be able to handle more and more tasks without us having to re-architect everything. And finally, accuracy. The task has to run pretty close to the time it was scheduled for. A few seconds late is okay, an hour late is not.
Now, whenever you're faced with this problem, there's a very, very common first idea. It seems super intuitive, but trust me, it's a trap. Let's walk through why it's such a bad idea.
The idea is just so simple, right? A request comes in to run a job in, say, 60 seconds. So you just kick off a timer on your server, timeout, done. And yeah, for one task on your laptop, that works perfectly. But in a real, live production environment with servers restarting and a huge load, this approach is basically a ticking time bomb.
This whole thing just falls apart in three really critical ways. First, these timers just live in the server's memory. So what happens if that server crashes or needs to restart for a patch? Poof, all those scheduled tasks are just gone. That completely fails our reliability goal. Second, every timer takes up resources, maybe a whole thread. That's just not going to scale to millions of tasks. And finally, it makes our servers stateful. That's a fancy way of saying we can't just add more servers to handle more traffic because the tasks are tied to specific machines. We've completely lost our ability to scale.
So if timers are the wrong tool for the job, what's the right one? Well, the real solution requires this fundamental mental shift in how we even look at the problem.
And here it is. This is the big aha moment. This is the whole key. A scheduled task isn't a running process or a timer waiting to go off. No, it's just a piece of data. It's just an entry in a database somewhere that says, hey, do this thing at this specific time. Once you get that, the whole scalable design just clicks into place.
So here's the new blueprint. Step 1, a simple stateless API gets the request. Step 2, it immediately saves the task details, what to do and when to do it, into a durable database. Now that task is safe, it's not going anywhere. Then step 3, we have a totally separate fleet of servers, we'll call them workers, that are constantly asking the database, hey, are there any tasks that are due right now? And finally, step 4, when a worker finds a task that's due, it grabs it, claims it, and runs the job. See how this decouples scheduling from execution? It's simple, it's stateless, and it's super scalable.
Okay, this architecture is really powerful, but it's introduced a brand new problem, a new bottleneck. How do our workers efficiently find the tasks that are due right now without killing the database?
Just imagine a single giant table with billions of tasks in it. A query like select star where execute at less than equal to now would be an absolute disaster. The database would have to scan tons and tons of data every single second. It would just grind to a halt. So how do we solve this? Well, there are two really excellent patterns to solve this exact problem. First is what we call time bucket tables. Instead of one huge table, you create smaller tables for each time window, like a tasks _2024 _05 _15 _1030 for all the tasks due at 1030. The workers only ever have to look at the table for the current minute, which is super fast. The second approach, and one that I really love for its flexibility, is to use a Redis sorted set. This data structure is practically tailor-made for our problem. The Redis solution is so elegant because of this one command. It's beautiful. You store your tasks in what's called a sorted set, and you use the execution timestamp as the score. Then, to get all the tasks that are due, you just ask Redis for everything with a score between 0 and the current time. This operation is lightning fast, unbelievably fast, even with millions of items, because this is exactly what Redis was optimized to do.
Okay, so we figured out how to store the tasks and how to find them efficiently. Now we need to design the workers themselves, the things that actually do the work. And they need to be both smart and incredibly resilient.
And here we hit a classic distributed systems problem, a real nasty one. At the top of the second, you might have dozens of workers all pulling the database at the exact same millisecond. And they're all going to get back the exact same list of due tasks. If we're not super careful, they'll all try to run the same task. You'll end up sending 5 reminder emails instead of just 1. This is called a race condition, and we have to prevent it.
The solution is to use what's called an atomic operation. You can think of it as an action that is guaranteed to either succeed completely or fail completely, with absolutely no in-between state. So when a worker finds a task, it tries to claim it by atomically updating its status from, say, pending to running. The key is only one worker can win that race. Only one will succeed. All the other workers will see that the status is already changed and just move on. No duplicate work, problem solved.
But what if a task fails? Maybe a downstream service it depends on is temporarily offline. We don't want to just give up, but we also don't want to just hammer that failing service over and over, making things even worse. The smart play here is exponential back-off. We retry the task, but after each failure, we double the waiting time. Wait 1 second, then 2, then 4, 8, and so on. This gives the other system a chance to recover.
And if a task keeps failing, even with all our smart retries, maybe there's a permanent bug. We need a final safety net. After a certain number of failures, we move the task to a dead letter queue, or a DLQ. This is basically a holding pen for broken jobs that need a human engineer to come and investigate. It's crucial because it prevents one single bad task from clogging up the whole system.
Okay, so let's pull all of this together. If you're ever in a system design interview and you get asked this question, here is your roadmap. This is how you give a brilliant answer.
First thing, right out of the gate, identify and reject that naive timer approach. Explain exactly why it fails at scale. Second, deliver your core principle. You have to treat tasks as data. Third, dive deep on the database query problem and propose a really efficient solution, like using a Redis sorted set. Fourth, you have to address the concurrency race condition and explain how you'd solve it with atomic operations. And finally, show that you're thinking about real-world failures by designing in resilience with retries and a dead letter queue.
And that's it. That's the architecture of a robust, scalable, delayed task scheduler. So, the final question I want to leave you with is this. This pattern, this producer-consumer model with a durable queue, is one of the most powerful and common patterns in all of software engineering. Now that you understand it, what else could you build with it? Where else have you seen it? Think about it.